So, Chapter 14 of Young and Freedman's University Physics is on fluid mechanics, and the first section is on density. A lot of the stuff in this chapter is very common, everyday stuff you probably encountered in a high school science class, and not too hard. No reason why it has to be this far into the book. It's just we're just now getting around to it. So the first section of this chapter is on density. Again, density is a fairly common concept that we understand. It's mass per volume. So air has a fairly low density of the mass in the air per volume of air. Whereas, if you were to have a huge rock fall on your car, the density of your car would increase as it got compacted into a smaller space. So we understand density. It is how much stuff is packed into a particular space. So here's the formula. Now that's not a P, that's a Greek letter rho, R-H-O, row your boat. So rho is the symbol for density, and rho equals m over v. That is, the density is the mass divided by the volume. And it's fairly standard. Of course, with something like air, it's going to vary. With any gas, as we'll see in visions of things to come, the density is going to vary depending on the temperature and depending on the pressure. But in general, at 1 atmosphere of pressure and 20 degrees Celsius, the density of air is going to be about 1.2 kilograms per cubic meters. It's cubic meters because it's 3 dimensions. The area or the volume of something is its length times its width times its height. So if you have a cube of a meter cube, the volume of that is going to be the width times the height times the length, or whatever you want to call the length or the width. But basically that's where we get the idea of a cubic meter. So that's the standard for air. Now for water, and water is actually the standard measurement that everything else, the density of everything else is compared to water, usually. On the next slide you'll see that. But basically water is 1,000 kilograms per cubic meters, 1 times 10 to the third. By the way, it's very common to use grams per cubic centimeter, and so to go from kilograms per cubic meter to grams per cubic centimeter, you just divide by 1,000, or 10 to the third, as it were. Okay, gold, just to give you something to compare it with, gold is 19.3 times 10 to the third kilogram per cubic meter. And so the density of gold is about 19 times as dense as water is. I guess osmium is the densest element of all the elements. Okay, well, average density is then, it looks to what, as the substance of a whole, what is the substance of a whole, its mass per volume as a whole. But of course, if you look at something like the ocean, if you're trying to figure out the average density of the ocean, obviously it's going to be much denser at the bottom of the ocean, I think, than it is at the top of the ocean, and so forth. So average density shouldn't be that hard of a concept to get your mind around when something isn't homogeneous, but kind of varies. A piece of wood might have a knot that's more dense than the rest of the wood. So average density looks to the overall mass per overall volume. Final thing in this chapter is a concept called specific gravity that I think we'll all agree with Young and Freedman is very poorly named. But it's been around. It's a term that's been around for so long that we seem to be stuck with it. A better term than specific gravity would be relative density, or density relative to water. That's basically what the specific gravity of a substance is. It is the density of a substance relative to water at 4 degrees Celsius. So because you're dividing a kilogram per cubic meter by a kilogram per cubic meter, or whatever, all the units cancel out. So specific gravity is a pure number without units. It's basically the ratio of the density of a substance to water. And so you'll find charts that give you the specific gravities of various substances. So that's the first section of this chapter. Pretty easy, wasn't it?